Bismillah ar-Rahman ar-Rahim. This new video concerns inverse function and some important properties. So let's us start with lemma 01. So let A and B be two subsets of R. Then let F be a bijective and strictly monotone function. Then f minus 2 minus 1, the inverse function of the bijective one, is strictly monotone and in the same monotonic as f. So if f is increasing, so f2 minus 1 is increasing. If f is decreasing, f2 minus 1, the inverse function, is decreasing. How we can prove this? So it is simple. Without loss of generality, we can suppose that f is strictly increasing. Let y1 and y2 be two elements of B such that y1 is less than y2. So here we have to prove that f minus 1 of y1 is less than f2 minus 1, the inverse function of y2. So we have to prove this strict inequality. Don't forget that our function f is bijective, which means that there exist x1 and x2, which are the element from A, such that f of x1 is equal to y of y1, and f of x2 is equal to y2. Let us proceed par contrapositive, which means that we will suppose that x1 is not strictly less than x2, but x1 is greater than or equal to x2. If we suppose this, we will get y1, which is equal to f2 x1, and y2 is equal to f2 x2, which means that if this is true, we will get a contradiction with y1 is less than y2. Don't forget that here we suppose by contrapositive. If we suppose that x1 is greater than or equal to x2, if we compose by f, we will get this inequality. And this inequality is not true. Why it is not true? Because we have firstly, y1 is less than strictly than y2, which means that if we have a bijective function from A to B, and if it is a strictly monotone, so f2 minus 1, the inverse function, is strictly monotone too, in the same monotonic as f. Let's move to the second result. Lemma 2, in this lemma, let E be an interval of R, and suppose that f is a function from E into R, which is strictly monotonic, and we suppose that f of A is an interval. This is a very important, very necessary condition. So we have to suppose that the image, the range of E by f is an interval. If we have the two condition, which means if our function is strictly monotonic and if the image, the range, is an interval, then necessarily our function is continuous on the interval E. How we can do this? Once again, we suppose that without loss of generality, we can suppose that E is not a trivial interval, which means E is not equal to empty set. Also, we suppose that E is not equal to A. So these two trivial cases are not considered here. Why? Because if we consider this, the result is obvious. Then we suppose that our function is strictly increasing. We can do the same with strictly decreasing, and let A be an element from E. And we suppose also that A is strictly greater than the infimum of E. And we suppose that A is strictly less than the supremum of E. In this case, we have to prove that the limit, if f is continuous, so the limit of f of x1x goes to A with from below, so we have to find f of A, and the limit of f of x, sorry, 1x goes to A from the above, so we have to find the limit equal to f of A. So we can just prove one result, and the second result is it can be done with the same techniques. Let us start supposing that A is an element of E, and we suppose that A is strictly greater than the infimum of E. By monotonic theorem, limit theorem, which is as the monotonic theorem of sequences, there exists a real L such that the limit of f of x is equal to L. This to be sure that the limit exists, and we have all the condition to the right to do this. Here, what we can suppose? We can suppose, since we goes to f from below, so we suppose that L is less than or equal to f of A. L actually, L, the real L, is the supremum of f of x when x is in A and x is less than A. So we try to prove that L is exactly f of A, which means that the limit, we are here, which means that the limit of f of x1 when x goes to I minus is equal actually to f of A. To do this, what we can do, we can proceed by contrapositive, which means that we suppose that L is strictly less than f of A, and we will get a contradiction. So, if L is strictly less than f of A, which means that there exists a constant M, which is between L and f of L strictly. Since A is greater than, since N is, since A is strictly greater than the infimum of A, we use the infimum characterization to say that we can find alpha in A such that alpha is less than strictly of A. But our function is supposed to be an increasing one. If it is increasing, this means that f of alpha is less than L, which is less than M, which is less than f of A. Why? Because alpha is less than a, so f of alpha is less than the limit when x goes to a. If it is true, so we will find this triple inequality. F of E is supposed to be an interval. If this is true, this is an interval. If it is an interval, so we can find C from E such that f of C is equal to M. Don't forget the condition. So here what we suppose that our function is strictly monotonic, and the second condition, we suppose that f of E is an interval. If this is an interval, so it has to take all the value between in the interval E. And since M is less than f of A and greater than L, L, which is the supremum of the set here. So we can find an element C from E such that f of C is equal to M. How about C? So here we have two cases. If C is greater than or equal to A, f is it is a function, an increasing function, and by the way, we will find f of C which is greater than f of A, which is greater than M. Don't forget that we have this hypothesis. The second case, if C is less than A, by the monotonic limits, we will find f of C is less than L, which is less than M. And this will takes us to a contradiction. Why it will take us to a contradiction? For the simple reason, f of C it have to be equal to M. So here it is strictly greater than M. And here f of C is strictly less than M. But don't forget that we find an element C such that f of C is equal to M, which is a contradiction in the two cases. We have not the equality f of C equal to M, which takes us to a contradiction. So this means that the limit of f of x, when x goes here, when x goes to A from below, is exactly equal to f of A, which means that f is continuous. And here we prove this lemma. Sorry. The third result, in this result, if we suppose that E is an interval, and this is a necessary condition of R, and we suppose that f is a function which is continuous and injective, so f is strictly monotonic. It can be strictly increasing and it can be strictly decreasing. So we proceed, I usually by contrapositive principle. So we suppose that f, it is not strictly monotonic, which means that it is not strictly increasing and it is not in the same time, it is not strictly decreasing. If we suppose that our function, it is not strictly decreasing, this means that there exist x and y from E such that x is less than y, but f of x is greater than or equal to f of y, which means that f is not strictly decreasing. Sorry. And we suppose that this our function is not strictly monotone. The second case, f is not strictly increasing, which means that there exists x prime and y prime from E such that x prime is less than y prime. But here we have not a strictly inequality. We have f of x prime is less than or equal to f of y prime. Sorry, French influence. This first stop, we start a new idea. The segment x prime and y prime, which are defined. So we have here a parameterization. So x prime is equal to t x plus 1 minus t x prime. T is in 0. We miss here 1. And y prime is equal to t y plus 1 minus t y prime. T belongs to 0, 1. If we take t equal to 0, here we will if we take t equal to 1, here we have 0, and here we have 1 times x, so x. If we take t equal to 0, so we have here 0, and here we have x prime, which means we parameterization of the segment x prime. The same thing for y prime. And here we define two continuous function. The first one is alpha, which goes from 0, 1 to r, such that t is equal to t x plus 1 minus t x prime. And the same for beta, which lies between y and y, between y and y prime. Here, alpha is a elementary function, so it is continuous. Beta is also continuous. And our function f, our function f is supposed to be continuous and injective. So if we take this composite function phi, which are defined by t f of alpha t minus f of beta t, this is a continuous function. Why? Because f, it is continuous, alpha, it is continuous, and beta, it is also continuous. So we can say that phi is a continuous function. And we remark that phi of 0 is equal to f of x minus f of y, which is positive or equal to 0. And phi of 1 is equal to f of x prime minus f of y prime, which is negative. We can show this here. Don't forget that we have this and we have this. Since phi is a continuous function and it is positive or equal to 0 at 0, and it is negative or equal to 0 at 1, by the mean of the mean theorem value, there exists T0, which belongs to 0 and 1, such that phi of T0 is equal to 0. And this means simply that f of alpha T0 is equal to f of beta T0. And this is a clear contradiction with the injectivity of f. Don't forget that we have supposed that f is an injective function. The supposition is here. So we proved we give a simple proof to this theorem. If we have a continuous and injective function, this means that f is strictly monotonic. Let us move to the last theorem and the main theorem of this session. The inverse function theorem for strictly monotonic function. Let E be an interval, and I insist E is necessary to be an interval to apply these results, except the first one, the first lemma. And we suppose that f is a function from E to R, and we put G equal to f of E. Then, if two of the three hypotheses are true, if two among these three are true, the two imply the third. For example, if 1 and 2 are true, so they imply 3. If 1 and 3 are true, so it implies 2. And if 2 and 3 are true, so they imply 1. The first hypothesis, if G is an interval and f is a bijection function, to tell the truth, we need that f is injective. Why? Because if it is injective, since we define G as f of E, so it is naturally surjective. So here we can replace bijection by just injection. The second condition, f is strictly monotonic on E, and the third condition or hypothesis is f is continuous on E. If 1, 2, and 3 are satisfied, then the inverse function is continuous, strictly monotonic, monotone in the same as f. Let us start the proof. Sorry. If 1 and 2 are satisfied, then f is continuous. This is the lemma 0.2. If 1 and 3 are satisfied, then f is strictly monotonic, lemma 0.3. If 2 and 3 are satisfied, then G is an interval. We use the mean theorem value. F is strictly monotonic, thus f is injective, and by the way, bijective. If 1, 2, and 3 are satisfied by the lemma 0.1, the first one, f minus 1 is strictly monotonic, in the same monotony as f. So f minus 1, the inverse, from G to I, realize a bijection from G on E. So f minus 1 satisfies 1 and 2. And this means that f to minus 1 is continuous. Thank you for watching. And to close this video, the above result can be used to solve problem as the follow, which is in the worksheet. Let f be a function from 0,1 to 0,1, and it is continuous function such that f of 0 equal to 0 and f of 1 equal to 1. We define fn such that it is equal to f circle f n times. And we suppose that there exists a positive integer, just one m, such that fm of x is equal to x. For all x in 0, 1, so show that f of x is equal to x for any x in 0, 1. So the above result can be widely used to solve this problem. See you next time.